So my name is Noelle Overby, and this is creating hemodynamic models of early heart valve morphogenesis. The heart starts beating as early as 22 days, and the hemodynamic forces associated with embryonic heart development plays an active role in the heart's development. So animal studies have actually linked disturbances in these hemodynamic forces with the development of heart defects. So what you see on the screen right now is a model of a human embryonic heart, and there's this region called the atrioventricular canal, and this is where, or AV canal, and this is where your heart valves will develop. Your heart valves begin as these mound-like structures, but as fluid is moving through the region in a period from 5 to 8 weeks, they start to elongate and form your actual heart valves. And so my project is basically about modeling this fluid region in the AV canal to better understand hemodynamics within this region and to better understand heart development and heart defects. So I have two different kinds of models that I will be presenting on. We have 2D tubular models that were created in this paper in 2010, and they basically represent diastole and systole within chick hearts. So they basically developed these models using dimensions from embryonic chick hearts that they took within their lab. And then I also have image-based models from chick hearts. We have a chick day 3 and a chick day 5. So here are the results for the 2D tubular models. You can see vortice formation, or I guess eddy formation, on these back sides of the cushions. And it was really important to capture these characteristics because these vortices are associated with valve development. The maximum velocity occurs once the cushions are reached in the tubes as well, which is also an important characteristic of the AV canal. You can see here the pressure across the two tubular models. The pressure in the atrial chamber is higher and the pressure in the ventricular chamber is lower. And then across the surfaces of the cushions, you see this drastic pressure drop. Another thing to note is that in these models, the maximum pressure is reached at the beginning of the cushions, and then the minimum pressure is reached on the far side of the cushion. And then basically the pattern is like high, a peak, a dip, really low, and then it goes back up a little bit, and then it's at that pressure within the ventricular chamber. The wall shear stress is fairly constant throughout the tube, but somewhere on the surfaces of the cushion, they peak, and this happens in both the diastole and the systole cases. Here are the streamlines and the path lines for the chick day 3 model. You can see here that the flow is relatively smooth. In fact, it's very smooth. You see the streamlines literally look like really smooth straight lines, and there's no eddy formation on the back sides of the cushion. However, you do see the maximum velocity occurring near the cushions. Here is the pressure. Again, if you plot the pressure across the cushions in the direction of flow, you see that the maximum pressure occurs in this first chamber, and then it drops drastically across the cushion surfaces, and then it reaches a low in the second chamber. And again, with the wall shear stress, we see that it's relatively constant in the contour, and then its peaks within the surfaces of the cushions, or on the surfaces of the cushions. Here's the chick day 5 model. You can see eddy formation on the back side of the cushions, and you can see the maximum velocity occurring once you reach the surfaces of the cushions as well. Again, it follows that pattern with the pressure where it's really high in that first chamber, and then it drops dramatically across the surfaces of the cushion, and then it's low in the second chamber. Again, the shear stress peaks on the surfaces of the cushion, and it's relatively constant everywhere else. So here are all of my results together, and I just wanted to say that they do follow kind of a similar pattern if you compare the pressure profiles plotted across the positions throughout the geometry, and then the wall shear stress through the geometry as well. I will say that future work will include extending these chick heart 2D models into 3D and further troubleshooting some of the quantitative values that we got in terms of pressure and shear stress for the chick heart models. Thank you so much for listening.